Hi everyone. In our previous lesson, we have studied the solving methods of some exercises in real analysis, especially on sets. Today we will continue our exercises, our solution methods. So, today we will study the problem-solving methods of limit points, isolated points, open and closed sets, complement of set, bounds, lower and upper bound, infimum, supremum, and the power of set. So let's start. So our first question is, we have given a set, an open set E, and we should find the limit point of E. This is our real number line, and this is our 0 and 1. So what is limit point? Firstly, let's recall the definition of limit point. So our definition is that let E be a subset of R and x0 from R if at the any neighborhood of x0 there exists at least one point of E distinct from x0, then x0 is called limit point of E. So this is our open set 0, 1, and if we want to draw a neighborhood around 0, we can find at least one point here or here that is from our set but is distinct from 0. Also, we can draw a circle around 1. This circle there are elements here from E which is included in this circle but is distinct from 1. So 1 is also a limit point. Inside of this set E, we can write, for example, 1 over 2. If we want to find out if 1 over 2 is a limit point or not, we should draw a circle around 1 over 2, and as is clearly seen that there are lots of points around the neighborhood, any neighborhood of 1 over 2 that is distinct from 1 over 2. So our answer is that, let me write, answer is that any point of E is limit point of E. So if we denote the set of limit points by E prime, let it be set of limit points of E. Then E prime will be the closed set 0, 1. Our next question. E is the set 0, 1, union 2, and union the open set 3, 4. Find the limit and isolated points of E. We gave definition of limit points in our previous example, and we find out that all the elements of this set are limit points of E, but here there is no isolated points. And let's solve this exercise. this is our real number line and our set 0, 1, 2, and 3, 4. Okay, it's clearly seen that 0, 1 we can find any neighborhood of 0 and any neighborhood of 1, that this neighborhood includes at least one point from E distinct from 1 or 0. Inside of this open set, any points are limit points. We proved it, we showed it in our previous example. And the set 3, 4 is also similar to this set. We can make a neighborhood, make a circle around these points 3, 4, or inside the open set 3, 4, any points, around any points, we can find a neighborhood that includes at least one point from E, distinct from this point. So 0, 1 and 3, 4 in this intervals, any points are limit points. But what about 2? If we make a circle around 2, you see that here we cannot find any points that includes to this set. Yes, but if we draw the circle large, yes, we can find points here, somehow here, for example. But what is said in our definition? If at the any neighborhood, okay, it means that we can draw the circle in any radius, okay, and in a neighborhood of this circle, this point should have a point from this set. So here this circle, this neighborhood, also that neighborhood does not include any point from E. Yes, so 2 is not a limit point, 2 is isolated point, but 0, 1 and 3, 4 are limit points. So if we denote the set of limit points by E prime is 0, 1 union 3, 4. This is limit points of E. What about isolated point? 2 is isolated point. Here is our next question. This is the set A, and this continues. So question is that actually claim is that we should show that 0 is a limit point of A. Yes or no? We should explain and why, the reason. So we must find a sequence points in A which converge to 0. Okay, let's find one sequence. For example, let it be delta n. As is clearly seen, our first example, first sequence is 1 over 2, 1 over 4, 1 over 8, yes, and etc. 1 over 2 to the n. It keeps going. So the limit of this sequence is 0. Yes, it converges to 0. So 0 is limit point of delta n. It keeps going and it never gets 0. Yes, it never been 0. Let's find another sequence. Let it be bn. Let's choose these points: 1 over 3, 1 over 9, 1 over 27. It keeps going. This is 1 over 3 to the n. Yes, as is clearly seen that this sequence is also shrinks. Yes, gets less and less, and it converts to 0, but it never be 0. So 0 is limit point of Bn. If we choose any sequence from this set, we will find out that all these sequences converge to 0. So our claim is true. Yes, our answer is yes. 0 is limit point of A. Next question is also about the set A. Is 1 over 2 a limit point of A? Okay, we should find a sequence from A that this sequence should converge to A. Yes? We want to find a sequence. For example, delta n in A with delta n should not be 1 over 2 and delta n should converge to 1 over 2. Answer. What's the answer? Since 1 over 2 is in A, but is not a limit point of A, then 1 over 2 must be an isolated point. So here we cannot find the element from A, the sequence from A that converts to 1 over 2, but 1 over 2 shouldn't be from A. Okay, then what is the answer? The answer is that since 1 over 2 is in A, but is not a limit point of A, then 1 over 2 is an isolated point. So let's find out the isolated points of A, also the limit points of A. So we have found out that the limit point of A is 0. Yes? What about the isolated points? All these points are isolated points. 1 over 2, 1 over 3, 1 over 4, and etc. It keeps going. All these points are isolated points. Okay, let's continue. Next question. We have a set A, as is clearly seen that A is neither open nor closed set. So our question is that, is 2 a limit point of A? And find all limit points and other isolated points of A. Firstly, let's draw a number line. Let it be 0. It's not included to A, and it is 2. 2 is from A. So let's draw a circle around 1, any circle. Okay, it can be like that, or it can be just like that. Every circle, every neighborhood of 1 contains a point in A. You know, here the right hand side of 1 contains at least 1 point from A. Yes, this is our set. The left hand side of 1 doesn't contain any element from A, but the right hand side contains any neighborhood of 1 contains at least 1 element from A. Also, it's true for 2. Okay, let's draw a circle, any neighborhood of 2 contains a point here on the left hand side of 2, and there is at least 1 point from this set. Yes, and this is other than 2, and therefore 2 is a limit point of A. If we just take a point inside from X, let it be X, any point inside of A, and any neighborhood of X contains, here let me denote it by red, okay, let it be here, any neighborhood of X contains an element from A. If we pick any point X, every neighborhood of X contains a point in A other than X. So our answer is that limit points, all points of A are limit points of A, but in this interval we have no isolated points. So limit points are 0, 1. Look at this interval, this is closed interval, and isolated points are not. Another question. Let it be the set A, which consists elements 1, 2, 3, 4, and 5. Okay, and the n is between 1 and 5. Question: find limit and isolated points of A. Okay, in order to find the limit point, we can choose the sequence from this set that converts to any point, and let's try out. It's real number line. This is 1, 2, 3, 4, and 5. Okay, if we draw a circle around 1, it doesn't contain 2, 3, 4, or 5. Also, if we draw a circle around 2, if we can find a neighborhood of 2 that doesn't contain any element from this set. Okay, also if we draw a circle around 5, we can find the neighborhood of 5 that doesn't contain any element from this set. So this set doesn't have any limit point, and all of these elements are isolated points. So limit point none. Okay, and isolated point all these points are isolated points. 1, 2, 3, 4, and 5. A finite set, remark, this is a remark, a finite set has no limit points. Okay, it's clearly saying that A is a finite set. We can count the element. The cardinality is 5. 1, 2, 3, 4, and 5. This is remark. A finite set has no limit point, but interval, an infinite set, has limit point. Okay, this is another exercise. Consider the set E is 0, 1, 1 over 2, 1 over 3, 1 over 4, and etc. It keeps going. Is the set E closed or not? And explain why. Let's recall the definition of closed set. What is the closed set? If all limit points of E is included to set E, then E is called closed set. If we denote the limit points by E prime, then E prime should be a subset of E. If this condition is satisfied, then we can say that E is a closed set. And let's find out here the limit point of the sequence 1, 1 over 2, 1 over 3, and the limit of sequence 1, 1 over 2, 1 over 3, and etc. is 0. Yes? And 0 is included in this set. 0 is element of E. 0 is element of E. So E prime is equal to just 0. It is the set of limit points, and 0 is from E. So therefore we can write that E prime is a subset of E. So E is closed set. We proved it. Our eighth question. Consider the set E is equal to the interval, closed interval AB. Show that E is a perfect set. In our previous lessons, we have proved that any interval, any elements of the intervals are limit point of this interval. Yes, let's show this. Let it be A, it's included. Yes, and let it be B. We have found in any neighborhood around A and B that it contains element from this interval. So A, B, and any element from this set is the limit point of the set E. Okay, so the E prime, what is E prime? Is the limit points of E is also AB. We have proved it in our previous examples. Example 5 and example 1 and etc. We have proved. And what is the definition of perfect set? Let's recall the definition of perfect set. If E is equal to E prime, what does it mean? If all the elements of the set are the limit points of this set, then it is called perfect set. And in our example, as is clearly seen that E is equal to E prime, so it is perfect set. Next one, let E be Q, the set of rational numbers. Is this set closed, or is this set dense in itself? And let's recall the definition of dense and in itself sets. If every point of E is limit point of E, then E called dense in itself. What does it mean? If E is a subset of E prime, if this condition is satisfied, then we can say that E is dense in itself. And here in our given example, the set of limit points of E, I mean E prime, is the set of real numbers. Yes, we have proved it in our previous examples. And since Q is a subset of R, hence we get that Q is E and R is E prime. We get that E is a subset of E prime. So E is dense in itself. What is the definition of closed set? If the definition of closed set is that if E prime is a subset of E, then it is a closed set. But here E prime R is not a subset of Q. Yes, and therefore E is not closed set. Next example, show that empty set is perfect set. So what was the condition of perfect set? E should be equal to E prime. Our set E is empty set. Yes, it has no element. What is the limit point of empty set? The limit point, the set of limit points is also an empty set. Yes, they are equal. Therefore, we get that E is equal to E prime. So empty set is perfect set. Next question. Is the set E is closed? The set E contains element 1 over 2, 2 over 3, and etc. It is the sequence is n over n plus 1. So the solution is, the answer is no. Why not? Let's find the limit of this sequence. Limit if n approaches to infinity. N to the over n plus 1 is equal to 1, because if we divide both sides, both denominator and numerator by 1, it gets to 0, this 1, this also 1, 1 over 1 is 1. And the limit of this sequence is 1, but 1 is not included to the set E. Yes, 1 is not from E, but the property was that if a set is closed, then its limit point is included to this set, but here the limit point is not included to this set. So E prime is 1, but E prime is not a subset of E. 1 is not from E. So this is the answer, the reason of the answer why this set is not a closed set. Okay, next example is about bounded sets. So we should find upper and lower bound of this set, and also infimum and supremum. So let's solve this problem. Let it be a real number line, and if S is x such that x squared is less than 11, let's solve this problem. We get that the square root of x squared should be also less than the square root of 11, and here x is the module of x is less than the module of 11, and the roots also are less than the square root of 11. Okay, it means that x is between minus square root of 11 and positive square root of 11. Let's show this in our real number line. This is the negative square root of 11, and this is positive square root of 11. And this this interval which is greater than the square root of 11 is upper bound, and this interval which is less than square root of minus square root of 11 is lower bound. So upper bound is the set which consists of elements y such that y is greater than the square root of 11, and the lower bound consists of elements Z such that Z is less than or equal to the minus square root of 11. And here the infimum is the greatest lower bound, okay, and the supremum is the lowest upper bound. Here we get that the supremum is square root of 11, the infimum is the square root of minus 11. As is clearly seen that this point is included, the upper bound starts from this point, okay, this point is included to the set of upper bound, okay, and the least element of upper bound is supremum of this set. This is upper bound. What about lower bound? The elements which are less than or equal to the minus square root of 11 are lower bound, and the greatest element of lower bound, which is a minus square root of 11, this is infimum of this set. So we found the answers. And what about this set? A is the interval from 5 to 8. We should find upper bound, lower bound, infimum, and supremum of A. This is our real number line. The interval is from 5 to 8. And we said that the upper bound is starts with the greatest element of this interval and keeps going on. Let's write like that. And keeps going. Okay? So the upper bound starts from 8 and increases 9, 10, 11 and keeps going. So this is K, that greater than or equal to 8. What about the lower bound? This is lower bound. Lower bound of these sets starts with 5 and decreases, okay? Lower bound. It is 5, 4, 3, 2, 1 and etc. It decreases, and they are K such that let it be K prime, okay, such that K prime is less than or equal to 5. And what about infimum and supremum? We said that the least element of upper bound, is supremum. So this is 8. 8 is supremum. The greatest elements of the lower bound is infimum. So the greatest element here is 5, because all other elements are less than 5. So 5 is infimum of these sets. We have found the upper bound, lower bound, supremum, and infimum of this set. Next question. We have a set S, and the question is that, is this set bounded? And let's recall the definition about boundedness. If a set has both lower and upper bounds, it means that if a set is bounded below and bounded above, then this set is bounded. Here our given set is bounded below and also bounded above. So let's find out why. This is below, sorry, this is my mistake, and this is above. Okay, if the set is bounded below, the greatest lower bound is 1, yes, and this set is also bounded above, so the lowest upper bound, let me write, lowest upper bound is 9, and 9 is greater than or the supremum is 9, this is supremum, and 1 is infimum. So this set has both supremum and infimum, and the answer is yes, this set is bounded. This is our today's lesson. Hope you can understand all of the question and their solutions. If you have any problem, any unclear part of the questions, please comment below, let me know, and I'll explain you again. See you in our next lesson.